Having given you the overview of the aldol condensation, we're now going to move into some of the nuances of this reaction. So specifically, if you do an aldol condensation with a ketone, there actually arises the issue of multiple possible products. So how does this come about? Well, so far, all of the ketone starting materials that we have seen have had only one type of alpha hydrogen. They have either been symmetrical, so acetone and cyclohexanone are both symmetrical ketones, the two sides of the carbonyl group are the same, or one of the alpha carbons has no hydrogens on it. So we saw acetophenone, and the alpha carbon that's part of the benzene ring, of course, has no hydrogens on it, otherwise you would have 5 bonds to carbon. And a similar compound, when you have methyl tert-butyl ketone, the tert-butyl group also has no hydrogens on the central carbon. So in all of these cases, there is only one possible enolate that can be formed because there's only one type of alpha hydrogen. But what about 2-butanone or methyl ethyl ketone? This ketone can form 2 different enolates depending on which alpha hydrogen gets removed. Okay, so indicated on this reaction scheme, we have HA and HB. So if you remove HA, you end up with the negative charge on the left-hand carbon. If you remove HB, you end up with the negative charge on the right-hand or terminal carbon. Okay, so loss of HA gives an enolate in which, looking at its alkene resonance form, the alkene is internal. The carbon-carbon bond is in the middle of a chain. If you remove HB, the carbon-carbon double bond in that resonance form is terminal. It's at the end of the chain. So these enolates, in this case, actually have a name. So from loss of HA, you get to what's called the thermodynamic enolate, because it turns out that that structure is more thermodynamically stable than the structure you get from removal of HB. More highly substituted alkenes, so in this case you have a tri-substituted alkene, are more thermodynamically stable than less substituted alkenes. And on the right-hand side, from removal of HB, you have a 1,1 disubstituted alkene. The kinetic enolate, when you think of kinetics, you're thinking about rates of reactions, and you may be wondering, what does that have to do with thermodynamic stability? Well, the kinetic enolate has its name because it is formed the fastest. And the reason why it would be formed the fastest is sterics. So HB, being a hydrogen on a carbon with 3 hydrogens that's at the end of the molecule, is more sterically accessible than HA is. There's only 2 hydrogens of type HA, and they are located closer to the center of the molecule. So it is a little more difficult for a base to access HA than it is for a base to access HB, especially, as we will see, if that base is large. Okay, so depending on which enolate you form, you will get a different product. So there are 2 possible aldol condensation products, assuming dehydration happens, which is the case that we want to be in if we're using a ketone as a starting material. On the left-hand side, we have the product formed from the thermodynamic enolate, and on the right-hand side, we have the product formed from the kinetic enolate. Okay, so as you can see, these 2 molecules are structural isomers of each other. So the question is, can we control which enolate we form, and as a result, drive the aldol condensation towards one product? The answer is yes, but it depends on which base we use to deprotonate the ketone. So the kinetic enolates are formed almost exclusively using the base LDA at low temperature. Okay, we met LDA briefly in a previous lesson in this unit. LDA stands for lithium diisopropyl amide. It's the conjugate base of diisopropyl amine, and with those isopropyl groups there, that nitrogen is fairly sterically hindered. So if it wants to gain a hydrogen, it's going to want to pluck a hydrogen that is more sterically accessible than one that is less sterically accessible. On the other hand, the thermodynamic enolates are formed preferentially. Notice I used a different word here, preferentially rather than exclusively, when sodium hydroxide is used as the base and the temperature is higher, room temperature or higher. Okay, so we have a set of conditions that favors the product, the kinetic enolate, and therefore the product from the kinetic enolate, and a different set of conditions that favors formation of the thermodynamic enolate, and as a result, the product that's formed from that. Now we've got to understand why this is the case. Well, deprotonation of the ketone with LDA is going to be fast and irreversible because LDA is such a strong base. Its conjugate acid has a pKa of 33, so we're looking at 14 pKa units stronger of a base than the enolate is. So if it does the acid-base reaction, that's why it's going to be irreversible. But then secondly, as we've already looked at, LDA is large, so it's going to go after the more sterically accessible hydrogen, which is HB. Deprotonation with NaOH is going to be much slower because NaOH is not really a strong enough base to deprotonate a ketone. And then secondly, that reaction, the deprotonation with NaOH, will be reversible. You might remove a proton, but then you're going to put it right back onto another molecule of NaOH and generate water. Eventually, everything will come to equilibrium, but it will take a while, and that equilibrium is generally going to result in a small amount of enolate. But what NaOH has going for it is that it is a small enough base that it can remove either HA or HB. So to understand a little bit more about what's going on here, we have an energy diagram. Okay, so this is potential energy versus reaction coordinate. The deprotonation reactions are going to go, but as you can see from the energy diagram, there is a lower activation barrier leading to the kinetic enolate, and that's because of sterics. So it can be formed at lower temperatures. Once the kinetic enolate is formed with LDA, that's where everything's going to end up. It's not going to go backwards. It won't reprotonate because LDA is such a strong base, you're not going to want to go backwards and generate more of that strong base. So in this case, the less thermodynamically stable enolate, the one that's higher in energy, can be trapped, so to speak. When sodium hydroxide is used as the base, will you form the kinetic enolate? Yes. In fact, you will probably form the kinetic enolate more often than you will form the thermodynamic enolate because the path leading to the kinetic enolate is an easier path. It's a lower hill to have to climb. But that reaction can and will go backwards. So you might form some kinetic enolate, but if you let it sit around long enough and come to equilibrium, the kinetic enolate that you form with NaOH will end up reprotonated, and then you'll be back at the ketone that you started with. At higher temperatures, so you see the energy barrier leading to the thermodynamic enolate is higher. At higher temperatures, you can overcome that higher energy barrier, and you can get to the thermodynamic enolate and form it. Once the thermodynamic enolate has been formed, reprotonation going backwards has an even higher energy barrier. So it is unlikely to take place. Okay, so at equilibrium, you will end up with a mixture of the ketone and the thermodynamic enolate as predicted by the strength of the base. In other words, with NaOH, you're still going to have more ketone than thermodynamic enolate, but you're going to have a negligible amount of kinetic enolate. Once you get to kinetic enolate with NaOH, it will go backwards. When you go to thermodynamic enolate, it will be less likely to go backwards. So that's why things are going to end up at thermodynamic enolate versus kinetic enolate. Okay, so the bottom line, the take-home message here is that with unsymmetrical ketones, the aldol product will depend on the choice of the base. And the selectivity is best if you use LDA and go after the kinetic enolate. But if you need the thermodynamic enolate, you have a reasonable pathway for that aldol product to at least be the major product.